This is a research to practice video that was prepared as a part of an initiative of the Geo-Environmental Engineering Technical Committee of the Geo-Institute. My name is Maria Chrysochoou, and I'm a professor at the Department of Civil and Environmental Engineering at the University of Connecticut. With my colleague, Assistant Research Professor Nefeli Bompoti, we will show a methodology for waste and soil fingerprinting using laboratory techniques including X-ray spectroscopy methods and microscopy. We have utilized these techniques in multiple research projects over the years. One research project focused on the application of various spectroscopy techniques to the characterization of construction materials in transportation and was funded by the Strategic Highway Research Project. The project website contains reports, publications, and webinars designed to provide practitioners with background on each technique and their applications, and is thus a great reference for those of you interested to find out more.
The objective of this methodology is to characterize solids, either waste or soil, or usually a mixture of the two, to investigate the origin of the contamination. In many cases, high concentration of common contaminants, such as heavy metals or others, would appear in the soil and would be of unknown origin. This is a common phenomenon around the world, with many industries facing this problem that often results to environmental liabilities. With the proposed methodology, solid samples with contamination or potential contamination from coal ash, steel slag, or other sources can be investigated, and the source of contamination can be determined. The laboratory method includes a three-step approach to characterize the samples. First, the elemental composition is quantified using X-ray fluorescence. Then, the mineralogy of the sample is determined through X-ray diffraction. And finally, the morphology is visualized with a scanning electron microscope. Each one of these methods provides a hint of the composition of the sample, and combining all of them together, we can draft a path to the sample's origin and sources of contamination. X-ray fluorescence provides information on the bulk chemical composition of the sample. The instrument required is an X-ray analyzer that is usually portable and can measure in situ concentrations of metal oxides and trace metals. The major advantage of this technology is the fast and also low-cost measurement of multiple elements. X-ray diffraction provides information on the mineralogy of the material, which is a characteristic of the material's nature. With XRD, the crystalline phases of the material are identified and correspond to a particular arrangement of atoms in a structure. XRD can be qualitative or quantitative if we include an estimation of the non-crystalline or amorphous content of the sample. The instrumentation required is a diffractometer and the software for the data analysis. We can use scanning electron microscope to visualize the morphology of particles that make up the sample matrix. When equipped with energy dispersive X-ray or EDX, it also gives the chemical composition of the observed particles. SEM may be used to identify particles of characteristic shape that is linked to a certain type of material. For example, fly ash is known to consist of perfectly spherical particles, or calcite crystals have characteristic hexagonal plates. For the sample preparation, the sample should be air-dried for at least 24 hours in a petri dish, usually under a hood. For the XRF, approximately 10 grams of trying material pulverized to pass a US-60 sieve will be adequate for the analysis. For our XRD analysis, a smaller amount, approximately 1 gram, is required, with further pulverization to a US 400 sieve. For the SEM, we can either use whole particles or even crushed material for our analysis.
We will now show you 3 examples of how the combination of the techniques was implemented to determine the origin of unknown materials. In the first example, we analyzed material obtained from a brownfield, characterized by the field geologist as urban fill. In this case, it was known that urban fill was mixed at the site with other deposited waste, and the consulting firm wanted to delineate the layers where more conventional urban fill stopped and other waste types began. The technique showed that urban fill had 3 characteristics. XRF indicated high levels of sulfur, arsenic, mercury, and lead, which are often associated with coal ash. The XRD yielded mineralogy consistent with a reference fly ash we had previously analyzed in the lab, with magnetite and cristobalite as accessory minerals. And finally, black coal particles consisting only of carbon were observed with the electron microscope. By analyzing a larger number of samples and using these 3 characteristics as a marker, we were able to identify the layers where this material was predominant. In the second example, we analyzed a black precipitate from a groundwater extraction well at a contaminated site, in which in situ chemical oxidation was applied. The precipitate analysis showed that it was almost pure manganese oxide associated with a treatment agent used at the site. This indicated the need to change the dosage and/or delivery method of the agent to prevent such precipitation. In the third example, we were called by the city of Hartford, Connecticut, to investigate the nature of white effervescence that was observed in the seams of a newly constructed brick wall in a park. The material was difficult to collect in sufficient quantities, and therefore only XRD analysis was performed. The XRD spectrum clearly indicated that the material was pure calcite. We concluded that the mortar used in the inseams of the wall contained excess calcium hydroxide, which leached out in the section of the wall that was not insulated. Upon contact with the atmosphere, the alkaline calcium hydroxide reacted with carbon dioxide, forming calcium carbonate or calcite. As there was no easy remedy for this problem, the city decided to go back to the contractor and rebuild the faulty section of the wall. These are only a few cases of spectroscopic applications in geoenvironmental engineering practice. To find out more or inquire about services offered by our lab, you may visit our website or contact me at maria.chrysochoou@ucon.edu.